All right, next is non-bonding electrons. Non-bonding electrons we've already talked about are valence, sorry, not valence electrons. Let me put this in this mode. Um, are what's called lone pairs. And they usually do not involve in regular type of bonding, but they can participate in bonding. Like if you have an H plus ion, these lone pairs can actually bond to the H plus ion, and you form the ammonium ion, which is one of the exceptions of ionic bonding. All right, and we'll talk about this when we talk about Lewis acids and bases. Lewis, I'm actually going to call it a base because it's a Lewis base, which is at the end of the chapter. Okay, so valence electrons not used are called non-bonding electrons or lone pairs. Nitrogen, for example, has one. Oxygen does too. They don't show you the example, but oxygen has two of them. All right, how do you form a covalent bond? All right, this is valence bond theory. And basically, how a covalent bond. So we always write like, you know, a hydrogen with a little stick in the middle. All right. If you look at a hydrogen atom, it does not have a little stick. It's not 2-8. Like if you were able to get a microscope that you can see atoms, hydrogens are not H's with a stick in between them. All right. This is actually what a hydrogen atom looks like. It's a blob of electrons. Okay, and basically the electron is in some sort of orbital, an s orbital, a p orbital, d orbital, f orbital, and then you have this overlap. So this sphere of electrons right here kind of overlaps with this sphere of electrons, so that, and it's not, you know, it's not arrows. Electrons aren't arrows. It's just showing you that the spin of this is going one way. Okay, let's say it's going this way, and the spin of this is going the opposite way, and when they come together, they kind of like cancel each other out, and you get this overlap right here. You kind of see that overlap region right there, and that's what a covalent bond is. And this is technically what it looks like. It has this kind of a, you know, this kind of shape to it where they're overlapping each other. All right. In this case, this is what's called a sigma bond. It's what's a head-on bond, or what they talk about is a cylindrical symmetric bond. It's called a sigma bond. Sigma bonds are some of the strongest bonds. Okay. So let's see what they say. I just want to see what their notes are. Electrons are pair overlapping. We just talked about that. Okay, great. All right, so carbon, what happens with carbons? All right, carbons do the same thing, but they do what's called hybridization. All right, I have a separate video all about hybridization that I recommend that you watch. We will go over this in class in much more detail. It's very hard for me to talk about it on these videos, but in class we will go over this. You will understand hybridization. Okay, if you have taken it before and you kind of don't understand it, don't worry. You will understand it after watching the video and watching a lecture in class. If you have no idea what it is, you don't know that you don't know that you don't know it. I don't know if that made sense, but it was kind of fun to say. But you will know it, okay? And this is what carbon does when it forms a molecule. All right, what happens is it hybridizes because carbon wants to make 4 equal electrons. So what happens is the 2s orbital of carbon and all of the p orbitals, they mix. These 4 orbitals come together and they hybridize. Hybridization means a mixture of things. Like we are perfect hybrids of our mother and father. Okay, half of our genes come from our mother, half of our genes come from our father. They mix them and they get you. So you are a hybrid of your parents. Okay, so when you mix all 4 of these, you get this, okay, which is 4 hybridized orbitals. And if you notice, I'm going to draw bonds. These are in a tetrahedral formation. Okay, now let me talk about this wedge and dotted line. I forgot to talk about it when we were in the Kekule chapter. But if the atom is coming out towards you, out of the plane, I'll kind of show you. You kind of draw this wedge. That implies the atom is coming out towards you. It's trying to draw 3 dimensions on a 2-dimensional structure. Dotted line means it's going back into the page, and then the solid lines means it's in the plane of the page. Okay, so if you were to take all these shapes and you combine them together, this is what you actually get. Okay, don't worry about this. If you're really curious, I can talk about that, but I'm not going to talk about it right now. And you get these 4 equal energy orbitals, and we call them sp3 orbitals. Okay, so this is a PY, this is a PZ, this is a PX, this is an S. You mix them together and you get sp3. Why is it called sp3? Because you combined an S and 3 different p orbitals together. So it's the mixture of an S and 3 different p's to give you sp3. That's what it is. The 3 does not mean the number of electrons in this case. It just means that's how many orbitals were mixed. Okay, and you get sp3 hybridized carbons. Okay, so here's a perfect example. Here's a carbon. This is methane. CH4 is the structure. You have these bonds right here are from hybridized orbitals. All right, the bond angle is roughly 109.5. Don't worry about the bond length. We're not going to worry too much about lengths. All right, and basically what this is you have this carbon with these hybridized orbitals. I'll try my best to draw these. Okay, and then you have hydrogen come in. Hydrogen will be our blue color. Hydrogen comes in with its s orbital. Remember, it's an s orbital, so it's a sphere, and it overlaps just like how we saw on bonding. Overlaps. So there's your overlap. Okay, and that technically is what carbon looks like. They're kind of showing you this kind of structure right here to kind of, in a way, show you that. But that's basically how it's bonded. It's these hybridized orbitals. So these are s, full-fledged s orbitals, okay, from the hydrogen. And then the red orbitals are sp3 hybridized, sp3. All 4 of these are sp3, okay? This is an sp3, this is sp3, that's sp3. So that is the structure. That's what they think is how these things structure. And I'll talk reasons why. When you watch that video, they'll kind of explain why they think this happens. Okay? So that is, and how do you know if something's sp3 hybridized? Well, you have 4 different groups around it. And the group could either be a hydrogen or a lone pair. So for example, ammonia, let's take ammonia for example. Ammonia has 3 bonds to hydrogen and it has a lone pair. And you might have seen in books that sometimes they put this lobe with the lone pair. That lobe is showing you a hybridized orbital. It's showing you this type of an orbital. All right. So this nitrogen is also sp3. How do I know it's sp3? Because it's attached to 4 different groups. So the 4 different groups are coming from an s orbital and the 3 individual p orbitals to give me a total of 4. Right? It's an s, a p, and a p for a total of sp3. Again, if you're not quite following this, you will in class. If you've already had class and you're watching this, this should be easy. You should already know this. All right, here's just kind of showing you the structure of ethane. Ethane is CH3CH3, or it's a carbon with 3 hydrogens attached to another carbon with 3 hydrogens. Okay. So you have, this is an sp3 carbon, and this is another sp3 carbon. These sp3 hybridized orbitals are coming towards each other to pair up the electrons. All right, so you have what's called an sp3, sp3, and this is a sigma bond because it's a head-on overlap. All right, this orbital is bonding directly to that orbital. The hydrogens, remember, are right here. So I have a, actually I'll draw on this molecule. I got a hydrogen here, a hydrogen here. Sorry if I'm not doing a blue, just that's kind of a pain to keep changing it. So here's where your hydrogens are with their S. So this would be called an sp3 sigma bond. Like, see how that bond right there is called an sp3 because one of the orbitals is an sp3 orbital and the other orbital is an sp3 orbital. So you have 2 sp3s bonding. This is an sp3 bonded to an s. So that's why you get ssp3. I guess you can say sp3s. I don't think I've ever seen that. I think they usually put the single orbital first. Okay, like I said, don't worry about the bond lengths. The bond angles, again, just assume it's 109.5. It does change a little bit when you get carbons in here, but for the most part, they're 109.5. Okay, now here is an sp2 orbital, same type of thing. So we've got, the 2s and the p's. So here's the 2s orbital, and then this is my px, my py, my pz. This is just a mixture of these 2. So I have a full-fledged p orbital still hanging out. And they're kind of showing you a top view of this. So you have 3 hybridized orbitals. So these green are the hybridized. So I've got an sp2, another sp2, and another sp2 in the back. And then, now I will use a different color just because I think it will make more sense. And then, perpendicular to this, we have a full-fledged p orbital. Remember, p orbitals are figure 8s shape. So that's a full-fledged p orbital. In this case, it's my py because it's in the y-axis. All right, that's how you get that. And then these are all sp. What do you think? sp3, sp2, or sp1? The answer is on here, and realize it's an s plus 2 p's, not all 3 of them, but 2 of them. So it's sp2. All right. So once again, I hope that makes sense. If we've already had class, if you haven't, then when you have class, this will all come together. All right, here's just some information. It's also a sigma bond. Let's see, are they showing it here? No, do they show it? Next slide. Yeah, so here, this overlap right here is sp2, sp2, sigma bond. Okay. However, let me just see what you have here. Okay, yep. That's a sigma bond. However, so remember, here is my p orbital right here, and here's another p orbital right here. All right, these p orbitals overlap side on. Okay, so it kind of shows you right here. You see how you have this overlap right there? Overlap. So it's basically a p orbital and another p orbital overlapping each other. Okay, that's a pi bond. That's what a pi bond is. Pi bond is when you have these 2 p orbitals coming together and bonding side by side. The green ones, the hybridized ones, are head-on overlap. They aren't side-on overlap, they're head-on. That's why it's a sigma bond. Okay? The pi bond is a side-on. All right, this is a little confusing. I don't like this because they're showing you that there's 2 pi bonds. It's not. This whole thing is 1 pi bond. So I would ignore one of these. So if you notice, I have a double bond. One of the bonds is a sigma bond, and the other bond is a pi bond, just like how they're showing you. You see how that sigma right there? This green part of it is the head-on overlap sigma bond, and then the red and the blue out here, orbitals, is a pi bond. It's a full-fledged pi bond. Okay, so sp2, sp2 sigma in the center. We talked about electrons in the sigma are centered between the nuclei. Electrons in the pi bond occupy regions above it. Right, that's why it's called a pi bond. Okay, it's not centered around the nucleus. It's just kind of being shared. Pi bonds are much weaker bonds. Weaker. They aren't as strong. So the more pi bonds you have, actually you can do a lot more types of chemistry with the pi bonds. sp orbitals. This is now when you start getting to triple bonds. This is a mixture, so we have an s orbital plus 3 p's. This is just a mixture of an s and one of the p's. So you have an s and a p, so you have an sp orbital, and then now you have 2 p orbitals, and they're trying to show you that in this picture. This probably looks really confusing, but let me try it this way. You have a carbon with, these are my hybridized, the red are the hybridized. Now let's change to the blue. And then you have a p orbital that's in the y-axis. And then let's change it again. Let's do a different color. I know, I'm going crazy. Which color? Green. And then you have another p orbital that's coming out of the plane this way. So this looks really confusing because it looks like the red is also a p orbital. Those are not. Those are sp hybridized orbitals. Notice it's not really a figure 8. One lobe is coming off of the carbon on one side, and the other lobe is coming off on the other. So like here's a p orbital right there, okay? And then here's another, sp orbital, and there's another sp orbital here. These, notice, are connected. So you have a p orbital this way and a p orbital that way. So that's what they're trying to show you here. The green, notice, are the hybridized, and then this is one of your p orbitals right there. It includes the blue part. And then here is the other p orbital that's kind of right there. All right, and then when these bond, you have a sigma bond right here, sp, sp, and then you have this p orbital is shared on one side, and then the p orbital in the other direction is shared on the other. I will make structures for these in class, and hopefully you'll be able to see them a little better. Let me see if I can try to do it here. Nah, I'll just do it in class. Don't worry about it. It'll make sense in class. Bond lengths, don't worry about. Bond angles, worry about. So it's 180 degrees because it's a linear molecule. All right. I like this chart because it just kind of shows you the difference in bond strengths. A lot of people think that, if I have a carbon-carbon single bond, and then if I have a double bond, it should be twice the amount of energy, and then a triple bond should be 3 times the amount of energy. It doesn't really work like that. Okay, if you look at a carbon-carbon bond, so the higher the number, the more energy. Okay, so notice a carbon, or the stronger the bond strength, the higher the number, the more energy, the stronger the bond. So carbon-hydrogen bond is actually a stronger bond than a carbon-carbon bond. All right, a lot of people don't realize that, but hydrogen is small. It does not want to be unpaired. It wants to be paired up with something. So notice a single bond, a carbon-carbon single bond, this is all I care about, is 377 kilojoules per mole. Don't worry about what the numbers mean. I'm just comparing the numbers. Now let's go down to a double bond. Okay, you would think the double bond should be twice as strong as this. If that's the case, if you take 377, and since I have 2 of them, and multiply it by 2, you get, I believe, 754. 754. However, that is not 754. It's 728. It's smaller. So why is it smaller? Well, it's because our sigma bond is 377. Okay, but the pi bond, I did these calculations, is 351. How did I get that? I just took 728, subtracted 377, whatever was left over is the amount of energy in the pi bond. So notice the pi bond is what, 26 kilojoules per mole weaker? That might not seem like a lot, but it actually is quite a bit. All right, and that's important because the pi bond is a weaker bond, and we're going to talk about that carbon with double bonds can easily do chemistry. All right, you can actually do a reaction on a carbon double bond. Carbon single bonds do not do a lot of reactions. Okay, this is even more apparent when you get to a triple bond. Okay, 965. All right, so if you do the math, the first one is 377, that's the sigma. Another one is 351, and then how much is the next pi bond? 237. 237. So it drops down even more. So triple bonds are actually weaker than a double bond, and double bonds are actually weaker than a single bond. All right, so I just kind of want to show you that because I think that's important. All right, we'll talk about 1.9 in the next video.